Welcome to a new video on my channel. This is Statistics 101. In today's episode we are gonna have a look at variance. In previous episodes we have already explored discrete and continuous random variables, as well as their expected values. I'll link the videos in the info cards. I would recommend you to watch them first. So let's dive straight into the definition of the variance and let's break it down afterwards so that everyone can afterwards compute variances. Let x be a random variable. The variance of x is then defined as the expected value of a squared deviation. Deviation is measured by the distance between the realizations of x to the expected value of x. Some properties to mention straight away are that since we are looking at squared deviations, we can deduce from that the variance must be greater or equal to 0. We will talk in a second about this and why this is required. Also, the larger the deviations of x to the expected value of x is, the larger the variance will be. That maybe sounded too complicated, so let's break it down part by part. So x minus the expected value of x is the deviation of the realizations of x from the expected value of x. So if the expected value is 0 and the realizations of x are minus 1 and 1, then we would have minus 1 minus 0 and plus 1 minus 0 as the deviations. Hence minus 1 and plus 1 are the deviations. They simply describe how far the realization is away from the expected value of x. Now we want to know what is the total deviation of all realizations to the expected value. If we would simply sum up those deviations, remember which are minus 1 and 1, then the total deviation would be 0. But that would be misleading since the realizations are not 0 themselves. So we do not want those deviations to cancel out because of sign differences. That's why we square those to make them positive. You can also picture that problem in another context. You got a function f from x that is plotted against x, and we have the following regression line candidate. So this line here. Additionally, we got a set of measurements represented by the dots. Our task is to find the optimal regression line such that the deviation from the regression line for any x is minimized to the set of measurements. The least squares method tries to minimize the sum of squared deviations. Because if it wouldn't be squared, then the measurements below the regression line and the measurements above the regression line would cancel out. Now we know why we need the squared deviation. If we will relabel this deviation as z, then the squared deviation becomes z squared. Finally, the variance of x is simply the expected value of those squared deviations represented by z squared now. So when we ask about the variance, we actually want to make a statement about the expected dispersion of the realizations in comparison to the expected value of x, right? Let's do an example in order to digest this dense piece of information. I wrote the definition of the variance in the top right hand corner for you not to forget it. So let x be a discrete random variable with the support of minus 1 and 1. The probability mass function is 0.2 if x is equal to 1 and 0.8 if x is equal to minus 1 and 0 otherwise. First we have to compute the expected value, which is simply 0.2 times 1 minus 1 times 0.8, which is equal to 0.2 minus 0.8. This is equal to minus 0.6. Now we construct a helper random variable named z that is defined as x minus the expected value of the x squared. The support is now minus 1 plus 0.6 squared and 1 plus 0.6, this whole expression also squared. Because we insert the realizations and the expected value into z. So our support consists out of two elements, 0.16 and 2.56. We also have our probability mass function, which is 0.2 if z is equal to 2.56 and 0.8 if z is equal to 0.16 and 0 otherwise. If we compute the expected value of z, we will get 0.16 times 0.8 plus 0.2 times 2.56, which is equal to 0.64. Well, this computation was a little bit nasty. The introduction of the helper random variable and the relabeling makes it sometimes hard not to forget to make any mistakes. But luckily, we can derive a better formula for the computation of variances, at least in the practical sense. When we have another closer look at the definition of a variance, we will see that if we expand the inner squared expression with the help of a binomial formula, we will get the expected value of x squared minus 2 times x times the expected value of x plus the expected value of x squared, which is equal to the expected value of x squared minus the expected value of x squared. Let's redo our computation from the previous example. So we already know that the expected value is minus 0.6, when the squared value of it is 0.36. That's the first value that we need. Now we need to compute the first term of our new variance formula. That can be obtained by simply multiplying out the probability mass function values times the realization squared. That will give us a 1. 1 minus 0.36 is 0.64 and is our final result. As we can see, no matter which definition we choose to use, the result must be the same. But this formula is more computation friendly. There's another thing that you should know about variances. When we have two real numbers a and b and a random variable x, then there can be shown that the variance of a plus b times x is equal to the variance of x times b squared. This can be shown by using the definition of a variance and solving the squared expression. When a will get cancelled out and b can be drawn out of squared expression, leaving b squared. Since the expected value is linear, we can simply draw b squared out of the expected value. The derivation is very neat and simple to follow. Do yourself a favor and try to redo the derivation without looking at the solution here. Let's do another example, but this time with a continuous random variable to see how we compute the variance there. So our support is the interval going from -1 to 1. The probability density function is 3 over 2x squared if x lies in the interval and 0 otherwise. So the expected value is defined as the integral going from -infinity to infinity over x times the probability density function f from x. Since our support is going from -1 to 1, the integral will also only go from -1 to 1, because that are the only non-zero contributions. We can directly insert the probability density function. We then just have to solve the integral and will obtain the value 0, since our integral boundaries are symmetric and our function is 2. We then have to compute the expected value of x squared. The computation is very similar and leads to a value of 0.6. The variance is then 0.6 minus 0 squared, which is of course 0.6. I hope you found this video insightful and helpful. Please like and subscribe. And if you have ideas for other videos that are interesting to you, write them down below in the comments. Thank you and see you the next time.